Okay, so we arrive at our final new section, section H.2, areas and lengths in polar coordinates. Now we're going to focus on areas with polar coordinates. So of course, area under a curve is a big deal in calculus, right? You have a lot of integration techniques that allow you to find antiderivatives to get areas under curves. And but now we're talking about areas in polar coordinates. So how many recall that? I mean, if I want to find the area under a polar curve, the scenario I'm talking about is right here in figure 2. Okay, so see in figure 2, you have a polar curve like r equals f of theta, okay, where r is a function of theta. This is no different like with x and y variables. Y is a function of x. If you treat y as a function of x, okay, well here we're treating a radius as a function of theta. So like for instance, that example we looked at where we graphed r equals 2 cosine of theta. Okay, that's an example of a polar graph. And we're interested here, you notice in figure 2 that we have a starting angle of theta equals A and an ending angle of theta equals B. Okay, so just, you have a beginning limit and an ending limit. We want to find the area under the polar graph from theta equals A to theta equals B. Okay, from those angles. And so the scenario that we want to use to get there is to take this area. If you notice here in figure 3, they take the area and they divide that area up into not rectangles like you learned in calculus 1, but in sectors, circle sectors. So they have like a sector of a circle there that has like the difference between, for that blue sector in figure 3, the starting angle is theta equals theta I sub I minus 1. The ending angle is theta equals theta sub I. And so delta theta is your difference in those angles. And then you have a radius. You pick some angle, theta I star, in between those two angles and compute the radius for it. And that defines your radius. And so it's like a part of a circle, what they're drawing there in figure 3. That's a blue sector of a circle. So you see, you can take the total area under the polar curve and break it up into different sectors of circles with different radii, and the radii depends on the value of the f of theta, and then you can add up those areas. So to get a Riemann sum. And I don't know if you remember, but how many remember that the area for a sector of a circle is 1/2 r squared times theta? If you look at figure 1, they have an angle theta there and a radius. That's a sector of a circle. The area of that is 1/2 r squared theta. How many maybe recall that formula? Maybe it's been a long time ago. Okay, Jacob recalls it, and Leping recalls it. And remember, if if you think of a whole circle, the area of a whole circle is what? It's pi r squared. So if you were to like, for example, take this formula here for area and substitute in hold on here, substitute in for theta 2 pi. If that's your sector of your circle is the whole circle, theta would be equal to 360 degrees, or 2 pi. And so that formula would reduce to area equals 1/2 r squared times 2 pi, which is pi r squared. That's the area of a circle. So, I'm just trying to make the formula a little more intuitive for you. But at any rate, now what we're going to do is in figure, we take, we want to find the area under the polar curve here in figure 2, and we take the area and break it up into different sectors of different circles of different radii, and then we're going to add up all those areas. And of course, the area for each, based on figure 3, the area for each sector, circle sector, is 1/2 r squared times delta theta. Well, r is equal to, it's a function of theta, right? Because it's based on the r equals f of theta. So we're going to add up all those little areas, and that's going to get us this Riemann sum. That's going to get us this Riemann sum. And as n goes to infinity, as we sample, as we divide the area under the polar curve more and more, and let n go to infinity, we'd be adding a lot of areas for different circles or sectors of circles. What would this Riemann sum turn into as we let n go to infinity? What's always true? If you let n go to infinity, the Riemann sum turns into well, not an infinite series. Renat, if n equals infinity, I understand what you're saying, but for a Riemann sum, an integral, right? That's right, Renat. I mean, an integral, right? The Riemann sum turns into an integral, and so it turns out then that we come up then. Well, I mean, this is what I'm saying. And so this shows then that it's plausible. This isn't an actual, I mean, it's intuitive proof, but it's plausible. It's plausible then. Let me just, hold on here, get out of my way here. I got too much stuff open. Let me close a few things out here. It turns out then that the formula for the area of the polar region, okay, the polar region is the region under the polar graph. That's this region in figure 2. The area of that polar region is going to be the integral from a to b of 1/2 f of theta squared d theta. But we often represent f of theta by just call it r. Okay, so it's two versions of the same. Now you will have access naturally to this formula on the final exam, right? Because you'll have access to it. And I think now what I want to do is let's look at a few good examples. So let's go to hold on here. There we go. Okay, let me give you a moment to copy this example down. Okay, so what we want to do here is we want to find the area of the right half of the region enclosed by the polar curve 4 plus 3 times the sine of theta. Okay, so what's the first thing that, to do this problem, what's the first thing you need to do? Graph it. Okay, so you can go to Desmos and graph this, and just for I already did it in Desmos. I'll just bring up my Desmos real quick here. Okay, so there is 4 plus 3 times the sine of theta in Desmos. And I had to adjust my window a little bit. So that wrench on the top right, you all know that's how you can adjust your X and Y axis. And that's a pretty good window. So this is what's called a cardioid because it resembles a heart. Okay, it resembles a heart, the shape of a heart. I mean, you know, it's an upside down heart, but you know what I mean. Okay, so there's a picture. So like what you would do in your homework or on the exam is you would draw this picture on your paper and then shade in the right half of that region. Okay, are there any questions before I move back to the solution? Okay. Okay, well then let's go back to the solution here. Okay, so what I did was I wrote this, drew the picture, and I guess, you know, I didn't show you exactly, but the highest value is 7 on this, and that makes sense because the sine of theta, becomes largest when, you know, the largest value of the sine of theta is 1. So, you know, it makes sense that 7 would be the high point. Okay. So let's remember what our so this is my polar graph right here. Hold on. This is my polar graph. And this is the shaded area that I shaded in here, okay? Now remember, what is our area formula? Our area formula is the integral from A to B of 1/2 r squared d theta. That's how you find the area of a polar region. So, okay, well, my radius is 4 plus 3 times the sine of theta. Okay, so that's my r. So 1/2 r squared. Oh, I forgot to put d theta here, didn't I? But now, what about the limits? I have a limit of negative 90 degrees to 90 degrees. Okay, let's see if that makes sense. Why is that? Well, let me show you. Let me show you. So our polar curve starts here. Starts there, right? At that point, whatever that point is. And if I were to draw that angle there, that ray, theta, what is it? What is that theta? When you're looking down, you're looking down what degrees? So 90 degrees. So theta, that's right. So theta starts at negative pi over 2. And then theta is going to take on all the values from negative pi over 2. What would the value here be, by the way, class, at this point? What would the value of theta be? Right here at this big red point. Theta, though, the angle theta. Theta would be 0. Well, you're right. Nathan's right that the radius is 4 there because theta is 0. So, but we keep going. The polar graph keeps going, keeps going, keeps going, keeps going. Theta keeps increasing, increasing, increasing until we get here. Well, when we get there, okay, when we get there, what's theta equal to there? 90 degrees. That's right, Leping. Okay, so far I hope we're good. Please let me know if you have any questions. That's why our limits go from negative pi over 2 to pi over 2. And now the rest is really algebra and calculus. But of course, we have to be smart in how we compute this definite integral. So 4 plus 3 sine of theta, that quantity squared, would be 4 plus 3 times the sine of theta times 4 plus 3 times the sine of theta. And if you FOIL that out, you'll get 16 plus 24 sine theta plus 9 sine squared theta. Okay, and I'll mention too, the 1/2 that was inside the integral, part of the integrand, I brought it out front. Okay, so what I'm going to do, I have the integral of the sum of 3 functions here. That's then the sum of the 3 integrals. And I bring the constants, well, the 16 I left in here, but the 24 and the 9 can come out of their integrals. Okay, are there any questions up to here? Okay. Well, now we have to decide, how. Let's compute these integrals. Okay, but sometimes you can exploit the geometry of your function and the limits to help you. So, like for instance, this second integral here, okay. Yes, I could get the antiderivative of the sine, that's negative cosine of theta, and I could then put in the pi over 2 and negative pi over 2. I could do that. But if I think about the sine wave looks like this, from negative pi over 2 to pi over 2, and we have positive area and negative area. What happens to the positive and negative area? They cancel each other out because of the symmetry of the sine function. The sine is an odd function. That's right, Leping. So I can just, put a 0 here. That saves me a little time, right? A little work. Now, what I do with, well, are there any, so far are we okay? Give me a thumbs up if you're okay so far. Okay, good. All right, well, now what's next is this sine squared of theta. Sine squared of theta, if I were to graph that, it would look like this. If I were to graph that on Desmos between negative pi over 2 and pi over 2, it would look like this function here. What seems to be true about the area on the left and the area on the right? What seems to be true about the blue area on the left and let's say the red area, or sorry, the blue area on the right and the red area on the left? What's true about those areas?
They're equal.
They're equal. Absolutely. And we can make use of that. We can make use of that. This area and this area, that's good, Maria. They're equal areas. Okay, so what I can do, you see, is I could put like a 2 here in front of the third integral and then change the bottom limit to what? To 0. Right, good Leping, good Renat. And that might make our life a little easier, right? It might make our life a little easier. All right, so when you're ready, I'll go to the next page then, and we'll finish this problem up. Just give me a thumbs up. Okay, V's good. Thomas, how are you doing? You feeling comfortable with this? Good, excellent, excellent. Good. Tall's feeling good. Thank you, Thomas. Baraka, how are you feeling with this? You're feeling good with this? Okay, Gloria, how about you? You're doing okay? Good. Jazi, how about you? Are you feeling this so far? Good, good. Okay, well, so let's go to the next page. I'm going to do this. I'm going to change the bottom limit to a 0 on that third integral and then double it. Okay, and so that's what I do. And see, having a limit of 0 is actually kind of nice. You know, it's easy to work with that limit as opposed to like negative pi over 2. I mean, you can do it. You don't have to do it, but I'm just saying. So, of course, now, the first integral, the antiderivative of 16 was just 16 theta. And then, okay, the sine squared of theta, we're going to have to use a trig identity, one of these double angle identities to help us. So the sine squared theta is 1/2 times 1 minus cosine of 2 theta, right? So, and naturally on the exam, you know, you have access to the formulas, right? You have access to them. There's a trig section in the appendix. In the back of your book, there's a trig section. I believe it's Appendix D. How many of you maybe referred to that Appendix D? No, it's not D. It's C. Okay, Maria has. Okay, and Michelle has. Good. Okay, wonderful. Yeah, any engineer would have access to that, and very good. So okay, you know, now it's just a matter of integrating carefully The antiderivative of 1 minus cosine 2 theta is theta minus sine of 2 theta over 2. And I just work things out. I work things out. This pi here comes from taking 2 times pi over 2, right? So for this second portion here, we substitute in pi over 2 and 0. And then the sine of 0, well, 0 is just because of 2 times 0. Okay, and we're just being careful. And when you work it out in the end, the area is going to be 41 pi over 4. And that's what WebAssign's going to want. It doesn't want a decimal. It does not want a decimal. It wants the exact answer. It wants the exact answer. Let's see. Nathan asks, is it possible to change the limits to 0 to 2 pi and then divide the integral in half at the end? The problem is, I don't know if, like, to draw that entire polar curve, I don't know, I guess you do need to go from 0 to 2 pi. I tell you, Nathan, I've never tried it. I've never tried it. I generally don't like doing that. I like my limits to start where the polar curve begins, and I like my limits to start where the polar curve begins, and then end where the polar curve ends. Anything else, it's like, I kind of don't know. It'd be like, that's like experimenting. I don't know. I don't know. I've never seen it done, and it could cause problems. It could cause problems. I think I would say no, don't do that. That would be my advice. It's, but I see why you're saying that, because 2 pi is a nice limit. But I would be, I don't know if it would work. But I know this works. Oh, Marcus, sine squared of theta, or sine squared of 2 theta, or sine squared of theta equals 1/2 times 1 minus cosine of 2 theta. That is a trigonometric identity. How many saw that maybe in Math 98 or one of the, like the trig class, or like maybe in their home school or wherever? How many recall those identities like that? Sine squared of theta. And Sean's seen it. Okay, Sean and Jacob's seen it. Yeah, it's a trig identity. And Marcus, in Appendix C, they have all the trig identities you'll ever need. Okay, in Appendix C. Okay. Okay, very good. Very good. So you're probably used to seeing like sine squared of x equals 1 minus cosine of 2x all divided by 2. You're probably used to seeing that. But, theta is okay. Well, that's fine. Theta is good. Okay, are there any other good questions before we move to the next example? Okay. Well, all right. Let me give you a moment to copy this example down. Okay, so in this problem, we want to find the area of the region that lies inside this circle, r equals 3 sine theta, and then outside the cardioid, r equals 1 plus sine theta. So what's the first thing we need to do for this problem? We need a graph. Can't do it without the graph. So what we have to do is we have to go into Desmos and draw both of these polar curves, polar graphs. So let me go ahead here and bring up then the Desmos. I've already drawn them in Desmos for you, but I'd like to kind of have it as part of the recording. Okay, so who can see Desmos okay? Is it showing up all right? Okay, good, good. So you see it's kind of nice. They have the circle in red. You can see there on the left, the circle is the red graph. And then the green on the left means the cardioid is the green graph. And you know, there you go. So, you know, what you would do, like if this were your homework or the exam, is you would copy this down on your paper, and you would, you know, you would proceed then to you know, solve the problem. So what's going to be, you think, what again, we don't want the entire area here. We want the area inside that red circle and outside the cardioid. Okay, so what do you think is going to be important to find? It's kind of always important to find when we have two curves together. What do you think we're going to need to find with respect to these two polar graphs?
Is it that whole top part between the green and the red from 2 to 3?
That's right. The shaded area would be the whole top part between the green and the red. That's right. And what do you think is very important to find? Points of intersection. That's right, Nathan. So let me go ahead back to the solution. Okay, and so I actually, here's where I find the points of intersection. Okay, so I set the 3 sine theta equal to 1 plus sine of theta, and I solve, and you know, sine of theta would have to equal a half. You know, so what I'm doing, of course, is I'm subtracting the sine of theta from both. I'll get to the picture in a minute, but so I'm subtracting sine of theta from both sides. And that's going to get me 2 sine theta on the left. So 2 sine of theta equals 1. And so sine of theta equals a half then. And, you know, if you think about your sine function, think about your sine function. Okay, where is the sine positive? Well, it's positive in the first and second quadrants. Okay, so you should know offhand that the sine of 30 degrees, sine of 30 degrees is a half. And so then the other angle, whose sine would equal a half, would also have a reference angle of 30 degrees, because reference angles, remember, are always measured from the positive, or they're measured from the x-axis, right? And so the other angle is then 150 degrees. Okay, and so that gets us pi over 6 and 5 pi over 6. And so when I draw my graph here, okay, the intersections here, you notice I draw, there are the intersections, okay, in red, okay, and I draw these rays, and this ray here is going to be theta equals pi over 6. That's the ray for that that goes through that intersection point, and the other ray that goes through the other intersection point is theta equals 150 degrees, or 5 pi over 6. Okay. And the shaded area is right here. Here's the, well, let me get this. I shaded the area. So notice the shaded area of interest begins at pi over 6. Okay, and then here, here's the one polar curve. It ends at 5 pi over 6, and same with the other polar curve. The other polar curve starts at pi over 6. Maybe I'll put that in purple. It starts at pi over 6 and ends at 5 pi over 6. Okay, and so this time, to get the area, you're going to have to do a subtraction. You're going to have to take the area you're going to have to take this area here and subtract this area to get the area that's shaded above. Okay, to get that sort of, I don't know what you call it, looks like a quarter moon. The shading here, the black shading, kind of looks like a crescent. How many have seen like a crescent moon up in the sky? Okay, Renat knows what I'm talking about. And all right, Gloria and others. So yeah, so this is a, this is a little bit like, kind of, remember the volume problems when, we would take one volume and subtract another volume to get the volume we wanted. Same kind of thing here. This integral of 1/2 times the quantity 3 sine theta squared would be this area. Okay. And you can see that based on the picture above. You can see that. I mean, on the picture above, if I traced out that area, that would be, if I traced it out, that would be that area there, right? And then you're subtracting this area here, which would be the integral where the radius is 1 plus sine theta. So, you have to, these problems, it's very important, these problems from section H.2 to set up the integrals carefully, because, otherwise, you don't want to waste time, right? So make sure your limits are correct and make sure you're subtracting in the right direction. Are there any questions? The 1 plus the sine of theta, that second area is, traced out here, right? So it's really important to take the time to draw the picture. I wouldn't try to get the graph in Desmos, but then copy that graph down on your paper, so you can do the shading and so forth, and to make sure everything's good. Okay, so I want to move to the next page. Let me know when you're ready. Let me know if you have any questions. Just give me a thumbs up when you're ready. We have to compute this. It goes without saying, 1 plus sine of theta, that quantity squared would be 1 plus sine of theta times 1 plus the sine of theta. And so when we FOIL that out, we'll get 1 plus 2 times the sine of theta plus the sine squared of theta. All right, once again, let me know when you're ready. We'll move to the next page. I suppose I could say here that this area minus this area would, it would give you that crescent shaped area up there. I guess I could say that, but it's fine. It's fine. You know that. Okay, so let's proceed on then. Let's proceed on. So now what we have to do is the 3 sine theta, that quantity squared, gives you 9 sine squared of theta. And the 1 plus sine of theta quantity squared, I FOIL that out and I get 1 plus 2 sine of theta plus sine squared of theta. So I try not to do too much at once. It's very easy to make a mistake on these kind of problems, okay? And it's easy to make a mistake. So you just want to be careful. So what I do then is I take, for the first integral, is I take my half and I take my 9, and you get 9 halves. I bring that out front of the integral, and then the 1/2 I bring out in front here. And at the same time, it's not, I'm going to be taking the integral of a sum of 3 functions here. Well, that's just the sum of the integrals. So certainly I can, write this as my next step. Okay, and that being said, um, so you see there are four integrals here, four integrals. Okay, and so I got integral. Maybe I'll just label the integrals. I got integral 1, integral 2, integral 3, and integral 4. Which two integrals have the same, are from the same family of 1, 2, 3, and 4? Which are of the same family? Okay, Renaud's saying integrals 1 and 4, and I agree. They both have sine squared. So, I could take 9/2 times that first integral, and then from there I can subtract the 1/2 times the fourth integral. 9/2 minus 1/2. So 9/2 times the first integral minus 1/2 times the fourth integral. 9/2 minus 1/2 gives me 8/2, which is 4. 4 is 8/2. So little things like that can save you a lot of work. Anytime you can combine integrals, the limits are the same, right, on all the integrals, so you can combine them. And now I have 3 integrals. I just cut my work down by 25%. So now that we're down here, Nathan's good, excellent, excellent. Now that we're down here, what's your attention focused on? We want to make this computation as easy as possible. What might be making things a little bit hard for this problem? Certainly we can get the antiderivatives. Well, and the sine squared of theta. Okay, the sine squared of theta. The identity for that is 1/2 times 1 minus cosine of 2 theta. So given that, I can integrate. I can get the antiderivative of the first integral. What's kind of making things though a little bit, what might be a little bit hard in the problem? What part of the integrals might make things a little bit hard? The bounds. That's right. Good, Renaud. The limits. So like, pi over 6, 5 pi over 6, those limits aren't like pi over 2 or 0 or 3 pi over 2. They're a little bit, they can get a little bit messy. We don't have to do anything. We can get the antiderivatives and put in those limits and away we go. But remember the first problem we did, we took advantage of the properties of the sine and the sine squared, right? So look what I can do here. On the next page, I drew a graph of the sine squared of theta. And well, actually, I drew a graph of the sine of theta. And of course, sine of theta is highest at, from pi over 6, which is, 30 degrees, right? Pi over 6 is, pi over 6 is 30 degrees. 5 pi over 6 is 150 degrees. So halfway in between is 90 degrees. That's 60 degrees away from 30 degrees and 150 degrees. So pi over 2 is exactly halfway between pi over 6 and 5 pi over 6. So the sine wave, is gonna, I just have a portion of the sine wave. Let me just see here, one moment. Yeah, drawn from, 30 degrees to 90 degrees. And then the sine wave goes back down to 150 degrees. But what do you notice about these areas here? If you split this region up along pi over 2, what do you notice about the area to the left and to the right? The red area and the blue
They're
area.
equal.
They're equal. Oh, that's great. Those are equal areas. And by the way, it's going to be the same then for sine squared, which I also drew above. So this means then we can break up the integral. We can, well, what I can do is, you see, instead of the limits going from pi over 6 to 5 pi over 6, from 30 degrees to 150 degrees, let me have the limits go from pi over 6 to pi over 2, and then double the value of the integral. I do that for the first and third integrals. Okay? Because the areas from 30 degrees to 90 degrees and from 90 degrees to 150 degrees are equal. So, and now I have that pi over 2 is a much nicer limit than 5 pi over 6. Oh, you can work with 5 pi over 6, but I'm just saying these are things that you have to kind of just sort of keep what's the word I'm looking for? Just keep an eye on. You know what I mean? You don't have to do this. You could work with the limits of pi over 6 and 5 pi over 6 and still get the right answer. But using symmetry when you can't always use it, but when you can use it, it can make your life easier. Please let me know if you have any questions. How many of you plan to try to use symmetry for when you do these problems from section H.2? Okay, Renard, Jacob, Nathan, Michelle, Gloria. Okay, a lot of people. Okay, Tal. Good, good. It's kind of like an analogy. It's like, I don't know if you ever saw the movie Iron Man. I don't know if you saw that with, gosh, I forget his name. Downey, something Downey, right?
Robert Downey Jr.
Robert Downey Jr. Okay, Maria knows right off the bat. Well, remember in the beginning, he had he had an Iron Man suit, but then later on he had a better Iron Man suit, right? Compared to the first Iron Man suit he had. So that's kind of what I think of this. I always like to think of analogies. This is like, like my new Iron Man suit here. These new limits, better, easier. Okay. All right, give me a thumbs up when you're ready to go to the next page, and we'll move to the next page and continue this. Okay, Maria's good. Barack is good. Jacob's good. Nathan's good. Laping's good. All right. Shazi, Gloria. Abidara. All right. So, okay. So now Naturally, for the first integral, we're going to employ the fact that sine squared theta equals 1/2 times 1 minus cosine of 2 theta. And this 1/2 here, thank you, Leping, this 1/2 I'm going to bring out in front of that integral. Okay, so I'm going to have 8 times, well, I'm going to have 8 times 1/2, right? So, okay, here we go. Here we go. Wait, hold on. One moment here. One moment, class. No, we're good. Yep, we're good. This is okay. This is okay. Yep, yep. 8 times 1/2, and then you know the second integral is just 1/2 times 5 pi over 6 minus pi over 6. But 5 pi over 6 minus pi over 6 is just 4 pi over 6, which is 2 pi over 3. Okay. So it's really just kind of bookkeeping here, and you know I'm going to want to see this work now for your final exam. You know, your submitted work. I'm going to want to see this work, just like I want to see your, you know, I want to see your work. I always need supporting work for, you know, sometimes like multiple choice, some of those don't need it because sometimes it's pretty intuitive, some of those, but this kind of problem I would need supporting work, you know, so. Okay, so now the antiderivative of 1 minus cosine of 2 theta is theta minus sine of 2 theta over 2. Okay, we're just moving along here. Now I'll mention I use braces here like this, okay, just because I wanted to be a little different than the parentheses, these kind of braces. But just remember, WebAssign will not accept those as grouping symbols. WebAssign will not accept these kind of braces for grouping symbols. It'll do it like for an interval of convergence, does it include the endpoint or not include the endpoint? But for grouping symbols, you always need parentheses. Even if it's like a lot of parentheses, you always need to have parentheses for grouping symbols. All right, so I get down to here and let me know if you have any questions. Okay. Absolutely beautiful, this math, absolutely beautiful. And you can see the pi over 2 is really helpful because like here, the sine of pi, what's the sine of pi equal to? What's the sine of 180 degrees equal to? 0. And here, the cosine of pi over 2 is 0. That's easy. And the sine of pi over 3, that's not hard. Sine of 60 degrees is just root 3 over 2, right? And the cosine of 30 degrees, that's not hard. That just equals, that also equals root 3 over 2. So smaller angles are always easier to work with. All right, and when you're ready, then let me know, and I'll move to the next page, and we'll finish this. We'll finish this problem. See, if we were using like Cartesian coordinates, I don't think we could, like these different these different types of polar curves. Uh, you know, could we find a Cartesian equation for those polar curves? Well, maybe, but the integration would be it would be probably impossible, you know. But with uh, uh, integrating with respect to theta, with using like the polar coordinates, it makes these kind of problems possible. And it's important because they, you know, they are, these kind of shapes are out there, right? They are out there, like in architecture and so forth, you know. If you have a balcony shaped like what we're doing here, like a balcony or something, you want to know its area, right? You want to know its area, you know. How much concrete do you need to pour, you know, for the balcony, that sort of thing. I mean, you need to find these exact areas. All right, are we ready? Are we ready to move on? All right, all's good. Bernard's good. Jacob. Okay, Maria. Leping, how are you doing? Good. All right. All right. Let's finish it up. So the area then, I work it out. Everything's in simplified radical form. How many think on the exam they might need 2 attempts to get this kind of problem right? Okay, I hear you. Okay. Very good, very good. Okay, so what I'm going to do is I'm going to distribute the 4 here to the pi over 2 and to the pi over 6, or minus pi over 6, and then to the root 3 over 2 over 2, and that'll get me 2 pi minus 4 pi over 6 plus 2 times root 3 over 2, because 4 divided by 2, you know, that's a 2 there, right, in the denominator. 4 divided by 2 is 2. And then we have the minus pi over 3 here. And then 2 times negative root 3 over 2 is negative 2 root 3 over 2. Okay, and oh wow, nice things happen here. We have a cancellation here. These are really equal to root 3, right? 2 root 3 over 2 is root 3, but that's fine. And then All right, then since I have a pi over 3 here, minus pi over 3, I'll write negative 4 pi over 6 as negative 2 pi over 3. Get a common denominator so I can combine those two fractions. And negative 2 pi over 3 minus pi over 3 is negative pi. 2 pi minus pi is pi. And that's the exact area. And that's what WebAssign's going to want. How many of you think this is really pretty beautiful math, what you're learning here with polar coordinates? Okay, excellent, excellent. Sean likes it. Bernard likes it. Paul likes it. Good. Baraka likes it. And you know, if you take multivariable calculus, which I really encourage, you know, after you know, this course is a gateway then to our 200 level math courses, and multivariable calculus with Math 280 will you know, you'll work with coordinate systems in three-dimensional space that are like extensions, like cylindrical coordinates are an extension, for instance, of polar coordinates, and that will you know, further enhance your math capability. So a lot of beautiful stuff, you know, a lot of beautiful stuff after Calculus 2. This course is really the gateway to higher level math. And, you know, I hope you enjoyed this section. Are there any questions? Okay, let me stop the recording for a moment.